Morning students. Today in chapter 6 we will be discussing about increasing and decreasing functions. Now which are the things to be discussed in this unit? First of all, we will discuss about the definition of increasing and decreasing functions, then graphical representation of increasing and decreasing functions, then the derivative test for a function to be increasing or decreasing, and we will be finding the interval in which the function is strictly increasing or strictly decreasing, and finally we will solve some of the problems on increasing and decreasing functions. So at the end of this session you will be able to find whether a function is increasing or decreasing in an interval. Then you can draw the graph of increasing and decreasing functions, and you will be able to find the interval in which a function is strictly increasing or strictly decreasing, and also you will be able to solve some of the problems on increasing and decreasing functions. So before we proceed to this chapter, what you know from the previous chapter, you know differentiability, and you know how to differentiate the various functions using sum rule, difference rule, product rule, quotient rule and chain rule. Then you can differentiate the different types of functions like implicit functions, then we have say modulus functions and some other functions, say second derivative we are well aware of. So this differentiation you people have learnt it in chapter 5. So using this differentiation we will be solving the problems on increasing and decreasing functions. Now coming to the meaning of increasing and decreasing functions. Generally we know that if something is decreasing, it is going downwards, and if something is increasing, it is going upwards. In terms of graphical representation, if the graph of the function is going downwards, then the function is decreasing. So graph of the function is going downwards, we say the function is decreasing. And if the graph of the function goes upwards, then it is increasing. A function is said to be an increasing function if the value of y increases with the increase in x. Here we can find as we go on increasing x, the value of y or fx we can say it goes on increasing. Similarly to the left of origin, as we increase x, the value of y decreases, the value of y decreases. So with increase in x, the value of y decreases. Now coming to the mathematical definition of increasing and decreasing functions. Now coming to the increasing function, a function y, or we call it fx, is increasing over an interval if for every x1 and x2 in the interval, if x1 is less than x2 implies f of x1 is less than or equal to f of x2, then we say the function is increasing in that interval. And the same function is said to be strictly increasing over an interval if for every x1 and x2 in the interval, x1 is less than x2 implies f of x1 is strictly less than f of x2. So this is the basic difference between increasing and strictly increasing function. In case of increasing function, so f of x1 may be less than or even equal to f of x2, whereas in case of strictly increasing function, once x1 is less than x2, f of x1 must be strictly less than f of x2. Now in decreasing function, a function fx is said to be decreasing over an interval if for x1 x2 in the interval, x1 is less than x2 implies f of x1 is greater than or equal to f of x2. So when x1 is less than x2, f of x1 must be greater than or equal to f of x2. And the same function is said to be strictly decreasing if x1 is less than x2, here we find x1 is less than x2, implies f of x1 is strictly greater than f of x2. So this is your f of x2, this is your f of x1. So we find that x1 is less than x2, implies f of x1 is strictly greater than f of x2. So in this case we say the function is strictly decreasing. Now we have the derivative test to find whether a function is increasing or decreasing in an interval. Let us say f be a continuous function on ab and differentiable in the open interval ab. Here it is continuous in the closed interval ab and differentiable in the open interval ab. Then if f dash x, that means derivative of the function, is greater than 0 for all x belonging to the open interval, then f is said to be increasing in the closed interval ab. And if the derivative of the function is less than 0 for all x belonging to the open interval ab, then we say f is decreasing in the closed interval ab. And if f dash x is equal to 0 for each x belonging to ab, this is your open interval ab, then f is said to be a constant function in that interval. And here in this graph we find that in this region f dash x is greater than 0, so fx is an increasing function. And here at this point and also at this point we find that the slope of the tangent will be parallel to x-axis. So that means the function is a constant function. And in this region we find that the derivative is less than 0, f dash x is less than 0, so fx is decreasing. Now how to calculate the interval or intervals in which a function is increasing or decreasing? Now to find the intervals in which a function is increasing or decreasing, we need some of the steps. So these are the following steps. First of all, we have to differentiate the given function. So find the derivative of the function. Then equate that derivative to 0. So after equating the derivative to 0, we get the critical points. So the points at which the number line will be divided into disjoint intervals. Now we have to form open intervals with the values of x, which we got after solving the first derivative and the points of discontinuity. So means equating f dash x to 0, we get the possible values of x, value or values. Then we divide the number line into disjoint intervals. Then in each interval we have to find the sign of f dash x. So if in a particular interval f dash x is greater than 0, then fx is said to be an increasing function in that interval. If it is less than 0, then fx is a decreasing function in that interval. So that means we have to choose any arbitrary value or arbitrary point in a particular interval and substitute that point in f dash x. If it is less than 0, then it is decreasing. If it is greater than 0, then it is increasing. Then we write the intervals of increase or decrease. And on this basis, now we'll solve some of the problems. Find the interval where the function fx is equal to minus 4x cube plus 18x square minus 27x minus 7 is increasing or decreasing. So this function is given. We have to find in which interval this function is increasing and in which interval it is decreasing. So for this we find the first derivative, also f dash x. So f dash x becomes minus 12x square plus 36x minus 27, and on simplification this becomes minus 3 into 4x square minus 12x plus 9. So this is the same as minus 3 into 2x minus 3 whole square, a square minus 2ab plus b square. So it is a minus b whole square. Now this f dash x is equated to 0 and thereby we are getting x is equal to 3 by 2. Now this value so obtained, put on the number line. Now this is the only value 3 by 2, so we put that 3 by 2 on the number line. Now we choose a point to the right of 3 by 2 and put it in f dash x, and we find that it is less than 0. Similarly, by choosing any arbitrary value to the left of 3 by 2, again substituting it here in f dash x, again we find that it is less than 0, because this is a perfect square, this is always positive. Positive multiplied by minus 3 is always negative. That means any value to the right of 3 by 2 or to the left of 3 by 2 that makes the first derivative negative. So we can say fx is decreasing to the left of 3 by 2 and also to the right of 3 by 2. That means we can say this function is always decreasing in the numbers, in the set of number line or in number system. Now find the interval in which fx is equal to tan inverse sin x plus cos x is increasing or decreasing in the interval 0 to pi by 2. So our function is fx is equal to tan inverse sin x plus cos x. Now first of all we find the first derivative of the function, that is your f dash x. So d du of tan inverse u, it is 1 by 1 plus u square, considering sin x plus cos x as u, into du by dx. So dx of sin x is cos x and dx of cos x is minus sin x. And this on further simplification becomes, taking cos x common, we will be left with cos x into 1 minus tan x whole divided by 1 plus sin x plus cos x whole square. And if we observe, so this is a perfect square, it is always a positive. This sin x plus cos x whole square is always positive, and this is added to 1. That means the denominator is always positive. So the sign of f dash x will strictly depend upon the value of numerator. Now we find that this tan x is less than 0 for all values of tan x is less than 1 for all values of x in the open interval 0 to pi by 4. So 1 minus tan x, it is positive. Cos x is also positive in the interval 0 to pi by 4. So f dash x must be greater than 0 for all values of variable x in the open interval 0 to pi by 4. So in the interval 0 to pi by 4, the function is increasing. Similarly, if we take the interval pi by 4 to pi by 2, we will find that this 1 minus tan x is negative. So cos x is positive. So positive into negative becomes negative. Negative by positive becomes negative. So that means f dash x is less than 0 for all x belonging to the open interval pi by 4 to pi by 2. So the function is decreasing in the interval pi by 4 to pi by 2. So that means we have divided this interval 0 to pi by 2 into two disjoint intervals, 0 to pi by 4 and pi by 4 to pi by 2. In 0 to pi by 4 it is increasing, and in pi by 4 to pi by 2 it is decreasing. Now dear students, some of the questions I have assigned as homework, so please try to solve these questions. Thank you.